Okay then, everyone, good afternoon. Hi, hello, how are you doing? Hope you're doing well. There's another 2 minutes pretty much till we get to the class time, but just getting their stream started as usual. We're good to go in just a bit. Hi, Austin. Hope you're doing good. Hey, Noah. Welcome back. Just another minute pretty much. Tatsuma, welcome. Hey, Preston. All right, guys. Sorry to hear that, Noah, but persistence is key. I bet you that you guys can figure something out if you just work it out. Hey there, Prue. Welcome back. All right, everyone. So now it's 12:45. Thanks again, as usual, for being here. It's always good to see you guys after the weekend. So we have a pretty straightforward plan and schedule for the next meetings and for today for sure. Right now, we're in the middle of talking about Chapter 12, which has to do with science and pseudoscience. We started off just by getting through some of the notes on last Thursday, and today we're going to continue to go through the rest of it. Next class, Thursday, what you're going to do is take your quiz on Chapter 12. So all that is listed in the syllabus and the calendar, but just to keep you aware of that, not to forget, Thursday this week, you'll have quiz on Chapter 12, which is about science. That's the last of the 3 quizzes. You just turned in your homework for the homework number 3, having to do with fallacies in advertisement. So now that's in, and we just have 2 more things, a couple more things. This quiz that's coming up, and then quiz number, the quiz that's coming up, homework number 4, and then the final exam. I'm not going to assign the homework number 4 until, like maybe a week or so, because I want you to still be able to focus on this upcoming quiz, and it also gives me a little bit of a window of time to finish grading the last thing. So that's just what we have. If there are any questions about any of those things or any kind of comments that you might have, feel free to let me know. But in general, I'm happy to help any of the questions that might pop up. So just to say again, you just submitted homework 3. I'll be grading that this week. You're taking the quiz on Chapter 12 next class. There will not be a lecture or any kind of formal live stream on Thursday. It's another day for a quiz or test, so that's when you're just going to be sent the test form in the same way that you've been sent them before, right before class time, and then you get that window of opportunity, or time, I should say, to finish the exam before the end. Prue, is there any extra credit in the course? That's a good question. I've been thinking of a way to try and add some extra credit to the class. So let me get back to you as the rest of the week goes on. I would like to try and make it possible, and I'll try to add some kind of at least 10 points or 15 points extra credit assignment. But I have to think about what to do, and I want to make sure to announce it, having thought about it a little. So let me get back to you. Remind me again on Thursday if I don't say it at the beginning, but I'll try to add something. So that's a good idea. Okay, so what you have is today's meeting on chapter 12. Make sure to take good notes and pay attention. And then we will have our quiz next time. Next week, we're going to start in on chapter 9, which is the last chapter of the book that we'll study. That has to do with ethics and moral decision making. So we'll have 3 meetings on chapter 9. I'll give you homework for assignment after you take your quiz this week, and then we'll get ready for the final. I'll distribute a study guide for that, and then we'll also, have 2 review sessions leading up into the final exam. Okay, so if that's all clear and well, then let's just get back into chapter 12, which is about science. Okay, so let me just review a couple of the points that were mentioned in the last meeting, and then we'll continue from there. First of all, science as a general concept, what is the definition? It's reasoning from observable facts to testable explanations for the facts. So, when you reason and you look at the world, you're trying to determine what the reason is behind things that you observe. What a scientist does is they first observe facts, things that are happening, and then we try to provide some kind of testable explanation for those facts, an explanation that gives the reason what caused those events or what kind of phenomena leads to those events. And then having had that explanation, we try to provide some mechanism by which it could be tested to see if it's the right analysis or the right explanation. So testable explanations for observed facts, that's what science is all about. We talked about some important figures in the early history of science. So right now I'm just like reviewing and recapping the stuff from last Thursday to bring continuity into the meeting. But yeah, we talked about some important figures in the early history of Western science. One example is Copernicus, who launched the scientific revolution with the discovery of heliocentrism. Heliocentrism was the discovery that the sun is at the center of the solar system and the Earth rotates around it along with all the other planets. Before this, geocentrism was believed to be the truth, and that was out of deference to the church, because according to the church orthodoxy, I would have wanted to put mankind right at the center of the universe instead of in a weird, random, non-central location. But, through observation, using telescopes, we were able to verify that that's not the case. So both Copernicus and Galileo had discoveries about heliocentrism. Galileo was persecuted for having said that. But anyway, today we know that that was correct. And that helped to launch the scientific revolution. So Polish astronomer Nicholas Copernicus, who lived from 1473 to 1543, is a major figure. There's also Sir Francis Bacon, who's often credited with having discovered or at least established the different steps of the scientific method. And he was a British philosopher and statesman who lived from 1561 to 1626. We're going to talk about the scientific method today in more detail, so that'll be related to what we say in a moment. After that, we all talked about what are some different assumptions behind science. For example, one assumption, empiricism, that the main source of human knowledge comes from the 5 senses and what we can observe. We talked about objectivity. This is the assumption or belief that we can learn about the universe as it really is, as it objectively is, and that we can discover that truth without any kind of bias. Materialism, another assumption of science, is the assumption that everything in the whole universe is just made out of physical matter, even including consciousness and the thoughts that you have in your mind. So if materialism is true, sometimes it's called physicalism, then in that case, everything's made out of matter. Matter boils down to atoms in the final analysis, pretty much, even though there are some subatomic particles. But anyway, essentially this means that everything's made out of atoms, even consciousness is, and therefore there couldn't be some kind of non-physical or disembodied consciousness like a soul. Another assumption of science is predictability, which assumes that the universe overall is orderly and predictable, which means that when you have established cause-effect relationships, that they're going to be permanent, they'll be repeatable, and they will never change. I gave an example of like me holding, let's say, a marker over the table, and I asked you to just give a wild guess what you predict would happen if I let it go. And most people seem to get the idea that I would that the marker would fall if I was to release it from my grasp. But I kind of stimulated your thought as to how you know that, and it seemed as though most people would revert to the idea that, well, we know because that's how gravity works, and gravity has always worked like that before. And when I pressed you a little further to say, well, why do you think gravity will keep working in the same way? All we could do is kind of shrug our shoulders and be like, I don't know, just because we think these laws are permanent. And when you get to that point, you realize that that's the kind of assumption that science makes, that in laws of nature, gravity, inertia, the laws of thermodynamics, properties of different chemicals in the periodic table of elements, that these things are known for certain, that they will never change, and that once the cause-effect relationship has been identified, that it operates in the same way, not just here, but for all places and for all time. And then one other assumption was the assumption of unity, which makes the idea that there's an underlying unity to the universe. So according to that thought, everything should be explicable according to one unified set of scientific laws. For now, we don't have that achievement yet of the grand unified theory, because we have the two disjoint realms of quantum physics and the general dynamics of moving bodies, which was discussed by Einstein. So hopefully someday we can build a bridge between those two related but inconsistent at the margin realms of science. Okay, then we talked about what are different limitations of science before we spoke on the relationships between science and religion, or the attitude that people can have about the relationship of the two. So for one, science is limited by assuming the existence of the external world, which I think is a safe and widely shared assumption, but I guess it's something that you can't absolutely prove. Setting that kind of very philosophical limit aside, science is also constrained by only being able to talk about what is either directly or indirectly observable. So if there were such things that could not be observed, whether that's dark matter or perhaps paranormal or supernatural things that some people believe in, then science could never give any kind of correct or even hypothetical answers to those thoughts, because those are things outside the realm of science, which is based on observation. And then some people also think that the assumption of predictability could be seen as a limit, because how, again, can you know for sure that natural laws remain stable for all time, since we haven't yet been able to access anything up until beyond the present, clearly. Okay, so after that, we talked about different views that people have concerning the relationship of science and religion. And so I'm asking you that. What are our different views about the relationship of science and religion? Let's tap in with you for a moment and just see if you can give me that answer based on the notes and your memory from last lecture. So let's see what you think. Some people, when it comes to science and religion and the disagreements that we see between them at times, what are different views that people can have with regard to those conflicts, or at least with regard to the two spheres, religion and science? Let me know. Let you insert yourself into the chat a little bit. So what some people think. It just takes a minute. Going into notes, looking at a book, thinking about your memory. But with all these people here, well, you can't necessarily trust that anyone else will do it but you. So, you know, if you want to do something right, you got to do it yourself. Go ahead and let me know. What is a different possible attitude that some people do have about the relationship of science and religion? And hello, everybody. Okay, Jonah. One view is that science takes priority over religion when the two conflict. Correct. So in some minds, when you see science and religion on different sides of any issue, whether it's creationism, evolution, the time point at which human beings emerged into the universe, was it back at the beginning, created in God's image, or was it billions of years later? Some people will say that if there are such conflicts or inconsistencies between the two, that we ought to prioritize the scientific explanation and reject the religious one. A different view, and then hi Ariana, welcome back. Another view, correct Jonah, is the opposite, that religion takes priority over science. So some people will say that if science and religion do not see eye to eye on anything, then I'm going to reject the scientific claim and go with the religious one. So whether it's the Garden of Eden, the biblical flood, creationism versus evolutionism, these are different areas where there seem to be at least disagreements and conflicts, and if you hold this other view, then you will side with the religious claim. Age of the earth, the age of mankind, and other facts like those. Another possibility, what's a third one? Who could tell me this? So Jonah, you've done the heavy lifting, but I think others know what some of the other mentioned attitudes are. So we've got science taking priority over religion, religion taking priority over science, or science and religion work with different topics, therefore they don't conflict. Okay, also correct. So some people think that when it comes to the two areas, they're not dealing with the same topics. That's okay, Jonah. No, I appreciate it. But to everybody else, get involved and start typing some things in the chat if you can. So anyway, the third possible view, science and religion deal with different topics. What could be the topic of science? Maybe somebody thinks it has to do with physical reality, natural laws, cause-effect principles, and objective things. But maybe religion, according to some anyway, has to deal with the subjective, the spiritual, and the moral. So maybe if that's the case, there's no real room for conflict because they're not even talking about the same topics. And a fourth possibility, maybe not Jonah, but that's good that you know these things. To all the others, show me what you know. Tell me what's this fourth possible view, which after all we did talk about and which is in the book. So a fourth attitude about the relationship is that they're compatible. Yes, prove. Some people think that between science and religion, when you look at the explanations that religion gives and you compare them to scientific theories, maybe there are no real conflicts because we're just not interpreting the religious scripture or message the right way. So in view of the idea that religion says that man was created within the first 7 days, and in the scientific cosmological view of the world, no, it took billions of years for physical situation to provide for the existence of human life. Well, these don't seem to be in agreement, but maybe you could expand your interpretation of what a day means when it's written in the Bible. It could just be an open-ended period of time, like an epoch of time that doesn't necessarily amount to a real 24-hour day. So anyway, these are the sort of menu of options that people do have, and people stand in one of these different camps. You're either strongly aligned with science against religion when they disagree, or vice versa, or you think that they don't have the same subjects, or that they actually can match and support each other, that they're somehow consistent. Now, from there, we continue on with chapter 12. Next thing is to talk about the scientific method. So we're going to go through all the different steps of the scientific method as they're presented in this book. And before I do that, I want to first state a claim that's made in the book, which I think is true, about how the scientific method has certain general similarities with the critical thinking process. So let me say this first. Similarities similarities between the scientific method and the critical thinking process. So you guys remember that way earlier in the semester when we talked about good additional comment, Preston. That's right on point for the right concept and definition there. Concerning this, going back, as I was saying earlier in the semester, there were these 3 stages or steps of the critical thinking process, if you may remember, and that had to do with experience, interpretation, and analysis. So here's how that process plays out. Just as I was saying, experience gives way to interpretation, which gives way finally to the final part of analysis. And in that process, you start off by just describing what happened, but not yet trying to say why or how. So you just note that some event has either happened to you or in general. Afterwards, you go further by trying to explain the reason why you think it might have happened, how or why, what caused it, what was the basic reason. And then afterwards, you take a chance to allow yourself to reconsider your prior interpretation. So if new information becomes available, or if the heat of the moment has passed and now you're being a little more rational and objective, then maybe you'll be able to replace your prior interpretation with a better one. Or you might accept it and say it was actually, I had good initial instincts and I think I had the right explanation to begin with. Now, how is that somehow similar to the scientific method? Well, like I was saying, the scientific method is sometimes split up into a different number of steps. I've seen it divided into 3, 4, 5 steps. Our book goes with 5. But there's 3 that are absolutely core to, the concept in general. And so those 3 core steps of the scientific method have certain similarities to the steps of the critical thinking process. So this is a critical thinking, and over here is scientific method. So the scientific method begins with observation. You just observe something in the world, you collect data, and you notice that something has happened. So like some event, some phenomena. It could be a lightning strike, it could be a volcano erupting, it could be some other observable fact about the world. But that's where you start. You just notice that something has happened, which you don't yet understand why. And if you're doing science, you move on to the next step, which is to try and create a hypothesis. What the hypothesis does is it tries to give some kind of reasonable, educated scientific guess that could explain why the observed event happened. So you see something happening, first step. Moving on from that, let's try to give an explanation, a hypothetical explanation as to why. Okay, and then finally, you don't just leave it at that. Oh, I got a hypothesis, so I'm done doing science. No, you actually have to test this hypothesis to see whether or not it can be verified or whether it will be disconfirmed. So that's the last part, is testing. Now, the 3 steps in the scientific method that we're highlighting here, although as I mentioned, you could expand it into a few more steps, they do bear certain logical similarities to these 3 steps of critical thinking in general. In critical thinking, we have experiences that we want to try and explain why they happen, and that we allow ourselves to further analyze or to reconsider. In science, we observe events, we try to give a hypothesis as to what causes it, and then we allow ourselves to test the hypothesis. The result of the test is that it may confirm the hypothesis, or the test may show that our initial hypothesis was wrong. So when you do a test, it's kind of like putting your interpretation under further analysis. You have a hypothesis which tries to explain what has been observed, but it may be either confirmed or disconfirmed by the test. And so critical thinking is kind of like science in the microcosm. We think critically all the time, even though we're not actually performing like scientific experiments, but the logical procedure of doing science has got these overall similarities. And that's mentioned in the book. I'll read it here, is what it says is the following. The scientific method involves the identification of a problem and the rigorous systematic application of observation and experimentation in testing an explanation for the problem. As such, it is similar to the 3 levels of critical thinking: experience, interpretation, and analysis that we studied in Chapter 1. Alone, experience or sense data tell us nothing. They have to be interpreted in the light of existing scientific knowledge and theories. Like the 3 levels of thinking, the scientific method is dynamic and recursive rather than linear, with analysis returning to observation to check for consistency, and observation being revised in the light of further analysis and observation. And the scientific method includes specific steps to guide a scientist through this process of analyzing their observations. Although there is some variation in the steps between the different scientific disciplines, the steps are basically as follows: identify a problem, develop a hypothesis, and eventually test it. So let's go now through the more precise list. Vanilla Ice, okay, that's a nice reference too. Let me go over the now precise steps of the scientific method one by one. Okay, so science. The scientific method. Okay, so we're going to go through all these steps, discuss them, and try and make that clear. Beginning with step 1, which is to just identify the problem. Okay, so with the first step, you have to start somewhere. You have to have a problem that needs to be solved. You have to have some phenomena that is not yet perfectly well explained, or the cause of it is not yet perfectly well understood. So identifying the problem is that. It is when you observe the world and you identify some as of yet unexplained phenomena. Okay, so okay, so you find something in the world, an event, an outcome, a fact that is not totally understood. There are many different possible examples of what this problem could be. Obviously, there's no shortage of different scientific understandings, inquiries, investigations. A couple that I could just refer to that are used in the book to give us something to think about as an example. Well, here's one. Bees globally seem to be in general decline in terms of like their overall numbers. So people who measure this fact have noticed a decline in the number of honeybees around the world. There's even a word that's been coined for it, which is bee colony collapse disorder. And it seems to be a problem because bees actually are a significant part of the, I don't know, biotic circle of life, whatever you would call it, the food chain. Yes, and colony death. And it's not even just limited to bees. I mean, the earlier editions of this book, like from 2012, they referred to the bee colony collapse disorder. But in the decades since then, with the newer version of the book, I think they should mention this, there's more general category of insects that are on the decline. So like a lot of insects are starting to just apparently lessen their numbers, thin out the herd, and there's fewer of them than we saw in the past. So it's a problem. It's something that we want to understand why it's happening. If we knew why it was happening, then maybe we could do something to mitigate it or to, counteract it or something. So anyway, take that as one possible example. Or, I don't know, you could say that there seems to be more intense hurricanes happening at this time in world history. Is that something that we observe? Perhaps. And then you might say, let's try and explain the reason for that. But sticking with the bee colony collapse disorder as our core example for now, that could be just something that we observe, and now we want to try and understand why. A scientist doesn't just say, hey, something's happening, isn't that crazy, and then just drops it. But they want to be able to understand the reasons why, or at least try to. So you start with something, a problem to be solved, a fact to be explained. After that, you go to the next step, and that's important step, step 2, where you develop an initial hypothesis. Develop an initial hypothesis. Okay, so first of all, what is a hypothesis? It's an educated scientific guess to explain the occurrence of an observed problem. So that's what happens at this stage. One tries to provide an educated scientific guess to explain the occurrence of the observed problem from step 1. Okay. You could imagine in medical science, maybe somebody, reports some kind of strange symptoms. They have an ailment. That's the identified issue. And maybe it's hard to diagnose what the reason or cause is. And so maybe the physician tries to reasonably give an educated scientific guess that might be the correct explanation. These initial hypotheses are tentative at first because you haven't tested the hypothesis. You haven't fully well analyzed whether it's correct by means of test and experiment. But you try and at least provide some reasonable sounding attempt to give the answer. And then there's further steps to follow. In bee colony collapse disorder, there you go, Paul. So that's one possibility. You might say perhaps the introduction of new pesticides or chemicals found within them are causing these wide-scale devastation to the bee population. What could be other possible hypotheses to explain this? Maybe somebody thinks that since it's traceable to the early 2000s, and it seems like that's when we started to see the phenomena, and that's also the time where widespread mobile cell phone technology starts to expand and proliferate. Maybe it has to do with certain cell phone tower frequencies that emit signals which are interfering with the life cycles or migratory patterns of bees. I don't know. Maybe it has to do with other changes to the ecosystem, like that introduce more invasive species that predate on these bees. Does it have to do with global temperature changes that are ushered in by climate change? So there's a whole host of possible hypotheses, but a researcher or research team or a scientist will try and settle on one of them at least initially. and make that the question that they're going to see. Is this the right explanation? So we got our first two steps now. Let's go ahead and say one thing, though, before I move on. I want you to know the difference between a hypothesis and a theory. There's a relationship, but there's just a little bit of difference. I'll put that up here, even though we're going to continue going through these steps. So let me just make it clear to everybody that what is a theory? It's nothing other than a very well-proven or well-established hypothesis. So a well-proven hypothesis. Well-confirmed, well-established through testing and through replication by other members of the scientific community. So what starts off as a hypothesis has a chance to graduate to the status of theory if it's one of the hypotheses that does not get rejected and it seems like it satisfactorily explains the problem and it's been well tested and experimented to verify that over and over again. So, a hypothesis may make it all the way to being a theory, but it has to be tested in the gauntlet of scientific research and replicated by others in slightly varied conditions. The difference between a hypothesis and a theory, yeah, I think it's something that is a subtle distinction that is lost on some people. A hypothesis is subject to major revision or elimination because it awaits further confirmation. But you do have to start somewhere. So a hypothesis at least continues the process forward. Let's go on then to the third step of the scientific method. And I got to clear the board to make that room. So like I say, the book, it chooses to divide the steps into 5. It's not always essential to have all 5 because some of them are in some, textbooks decided as more or less central than others. This third one here is one of those that you could say is an optional one, but since it's in our book, I'll definitely include it. And the third one is to gather additional info and refine the hypothesis if necessary. Okay, so meaning what? Meaning this. When you get your hypothesis, now you go out there and you start trying to collect data, and you're doing this in preparation for the ultimate test of the hypothesis. But sometimes in your initial data collection phase, after the hypothesis has been generated, you notice information that requires you to maybe make a slight edit or an adjustment to the hypothesis, tweak it in some slight way. So if that's necessary, you should do that, and that's the third step. So revise the hypothesis if necessary. Modify, like just not completely change it, but make slight adjustments to the hypothesis if necessary. Sometimes it won't be, but if necessary, then do that. And why? Based on initial data collection. Okay, so for an example, totally different case, but let's think of a different example. Paul, you're saying this, in step 3, during a potential experiment or while still creating, before the experiment, because you only are going to experiment on the refined hypothesis, the settled final version of it. So sometimes you gotta narrow it down a little bit and make it more specific or something. Here's an example. There have been some sociological studies which indicate that right now there seem to be higher rates of like depression and suicide among very young people. Like, so Gen Z, if you compare that against millennials and going back further, Gen X and stuff, it seems like there are just higher rates of mental, I don't know if I want to say it's mental health, but like problems with self-esteem, confidence, and your own sense of well-being. So more depression and et cetera seems to follow in this current generation. So that's something to observe. And you might ask why. Now, one person's hypothesis might be this, that this current generation is growing up on social media, and because we compare ourselves with other people on social media, and some of us have more followers than others, we start to judge ourselves in comparison to other people on these kind of websites. Some people think that that might be having some kind of corrosive influence on the mental wellness of young people, leading to these greater rates of depression and so on. I'm not saying I agree with any of that, but just as an example. Now, suppose that someone's studying this, And they're like looking at depression and suicide rates in different communities with different possible age groups and demographics. And they start to notice that there seems to be no significant correlation between social media use in general and higher rates of depression and suicide. But when they look at like specific types of social media sites, like photo sharing websites, Instagram, etc., that these maybe invite more negative comparisons against others, which lead to this kind of greater degree of like depression. So now what started off as social media engagement is driving teen depression rates is narrowed down and refined to social media sites that involve photo sharing as their primary mode of interaction are somehow driving up teen depression. Now that's still a hypothesis, not yet tested completely, but it's narrowed down. In another case, there have been a lot of school shootings, obviously, and back in 1999 when the Columbine massacre happened, that was like a really out of the ordinary event. But nowadays, unfortunately, it seems like it's more common, even though not so much over the last year when we've all been on lockdown. But now that we're going back into open society, we're starting to see a couple more of those, not necessarily always at schools. But anyway, what could be leading to that? Maybe one person's theory or hypothesis was that it has to do with gaming. But then they narrow it down into specific genres of games because they look at rates of, crime and the population of people who've done it and what their prior life experiences were, but they only see like any kind of statistical correlation between like shooter games and those kind of events. So anyway, not necessarily granting credence to either of these hypothetical examples, but in either case, well, actually there were some studies on the thing about social media and photo sharing websites being those that perhaps have a greater correlation with suicide and depression. But at any rate, in either case, you understand there was at least initially a hypothesis and it was somehow made more specific through the initial data collection. Don't listen to Tipper Gore about censorship in the media. Like, isn't that why we have all those warning labels on our, we used to have CDs and stuff. I don't think those exist so much anymore. So she fought the noble fight, but kind of for nothing. Or I don't know if it was really noble. I totally don't agree with some of that stuff. But yeah, gather additional information, refine the hypothesis. Let me read from the book a little bit, and you can just see some additional commentary. It says, since we cannot possibly take in all the data coming at us, hypotheses are used to guide and focus the collection of additional info. Without a hypothesis to guide the observations, we don't know what is relevant or what to ignore. The initial hypothesis may be modified on the basis of further observation. So it is vital that scientists strive to be as objective as possible and systematically record their observations without bias. And then here we have another case. As a graduate student in anthropology, Margaret Mead was interested in finding out whether the troubles that plague adolescents in our culture are also found in so-called primitive cultures. Her hypothesis was that in these cultures, adolescents would present a different and less troubled picture. To gather data, she lived with, observed, and interviewed 68 young women ages 9 to 20 in a small village in Samoa, an island in the South Pacific. And on the basis of her interview, she concluded that Samoan girls experienced a carefree adolescence and engaged in casual sex from an early age, a finding that shocked many Westerners. Many years later, the now elderly Samoan women who had been interviewed by Mead confessed that they had lied to her mainly as a joke. In this case, Mead's attachment to her hypothesis and her reliance on anecdotal evidence biased the way that she gathered information. So you don't want to be so overly attached to your initial hypothesis that you resist any attempts at modification. And that sometimes also has to do with confirmation bias. You're seeking confirmation so much that you're biased against evidence that your hypothesis might be wrong, or you're biased in favor of evidence that it might be correct, so that you take in the relevant information in a way that's somehow clouded by your bias. So scientists should also be objective as they consider revisions to their hypotheses. Yeah, I guess so. So Al Gore, I guess, undermined his wife's legacy through that, if you think about it. Okay, so that's step 3. Let's go ahead into step 4. And Noah, I don't know if you're still watching over there, but I hope so. I mean, earlier you were just going a little off the rails, talking about Shasta and things. We got business here in this class to take care of, so that's why I had to mute you for like 300 seconds, but I hope you come back. Anyway, step 4, test the hypothesis. Now, this is all important. This is one of the big ones, if you're going to point out any of the important steps. So testing the hypothesis. After you've got your narrowed down, refined hypothesis, the way that you think it should be, we talked about bees earlier, right? Maybe I can make one more example of part 3 involving the bee thing. You think bees are dying off. Let's say someone believed it was due to cell phone tower radiation. So they're going with that hypothesis. They think mass deployment of cell phone towers around the world has somehow interfered with the life cycle of these bees, and that's leading to it. But maybe they go into their research, and as they investigate this, they find that it's only certain frequencies that have any measurable effect on the bees. So what started off as cell phone tower radiation has become narrowed down to, like, I don't know, 5G cell phone tower radiation or something. So another case of narrowing the hypothesis, maybe. To number 4, testing the hypothesis. Okay, so finally you're ready to test it. Now what you're going to do is, either in a real world or a laboratory setting, put the hypothesis to the test. So you create an experiment that is either going to confirm or disconfirm the given hypothesis. All right, so okay, so you're going to perform a test. The test can happen in a real-world setting, or sometimes you're going to have a more controlled setting, like in a laboratory or something. And you'll conduct some type of experiment, which is going to have one of two possible outcomes. Based on the results of the experiment, you might see that your hypothesis has been confirmed. So the predicted outcome of the experiment was exactly what your hypothesis predicted. That would be confirmation for you. On the other hand, though, some hypotheses fail the test. You test it, and it does not seem like the predicted outcome by the hypothesis is what the test revealed. That would be disconfirmation, and that kind of sends you back to the drawing board a little bit. So you've done your test, and one last step, I guess, we can put in there is step 5, as the book puts it. And that would be to evaluate the hypothesis based on the results of the test. Okay, so let me give you that. Okay, so like I just showed you, when you test the hypothesis, you're going to have one out of two possible results. It's either going to be that it confirms, that the test confirms the hypothesis, or that it disconfirms it. So based on what result you get, there are two possible evaluations that you can make. So after the test, see whether you were confirmed or not by the test. If the test confirms the hypothesis, if the test/experiment confirms the hypothesis, then in that case, publish the results. You're done. Publish those results, forward them to the scientific community, and see if they can replicate your results for further confirmation. So then publish the results for further replication by other scientists. Okay, and on the other hand, if the test disconfirms the hypothesis, then let me ask you this. So say that the test does not confirm your hypothesis, it disconfirms it. That will send you back to an earlier step in this process. Which number do you think this takes you back to? So your hypothesis that you were working with, your test showed that it wasn't the right answer or explanation. So now, in that case, where should you go back to? You got to go back a few steps to where? Not number 3, actually, Devin, because your hypothesis failed. So it's not just like refine it a little more. I mean, I guess this is possible, but for the most part, let's try again. What do you think? If I didn't say it was 3, then what? Because, I mean, if your hypothesis has been disconfirmed, like thoroughly disconfirmed, then you should go back to developing another hypothesis. It's not initial anymore, I guess, in a sense, Noah, but it's another hypothesis. So if the test confirms the hypothesis, then publish the results for a replication by others. But if it's disconfirmed, then create a new hypothesis and repeat the steps. Going back to step 2. And you repeat. And so you're going to repeat steps 3, 4, and 5 until and unless you get a hypothesis that does get confirmation. I guess you could think that your experiment was flawed, yes, but I mean, I wasn't implying that there was a failure of the experimental design or methodology just in asking a question. I was just saying, suppose that you conducted a legitimate experiment and your hypothesis was not validated by it. If so, you still have the same problem to explain, but you have to try some different explanation for it. So like, for example, let's go back to the bee colony collapse thing. And let's just use the example of someone thinking that cell phone tower radiation is messing with the bees and causing them to die in big numbers. So question, how do you think you might design that experiment? Suppose this is your hypothesis. You think bees are dying because of cell phone radiation. So how could you perhaps create a controlled experiment to study this question? Or radio interference with bees, whatever. Good. Let me know though. What would be the test? You're the scientist, so design the test. What materials do we need? What kind of setup do we have to have? Sure, Paul, but this is one separate issue. I want to focus our mind on one thing, which is in order to explain this. And in order to do that, I would like to us all agree first on what the possible experiment could be. Okay, so you would have 2 groups, correct? A test group and a control group. So you would have one group of bees that were left exposed to a whole bunch of the cell phone tower radiation. So you just pump in a bunch to their controlled environment where it was bound to have any effect on them if it possibly could. And then you'd have another group that is not, as you put it, bombarded with radio frequencies or cell phone tower frequencies, whatever. And you'd have to now observe the effect on both. Now, if your hypothesis were correct, right? If your setting aside the subtleties and complex nuances there, Paul, which I appreciate, suppose that you had a fair experiment of this kind, where 2 groups of bees, one exposed to the radiation, one not. If just keeping it at this level of simplicity, what would count as confirmation for your hypothesis? So if your hypothesis is that the radiation of cell phone towers or radios are messing with bees, then what does it predict will happen in your experiment? Just a question. But you have to listen to me to answer this question, okay? The question is, what would count as confirmation of the hypothesis that bees are dying because of cell phone radiation in this test? If the test group that is being exposed to the radiation sees significant numbers of their population declining, okay? So according to the hypothesis, if this is the factor that's killing off the bees, then the group that's exposed to more of it should show some negative effects off of it. And the group that has no such exposure, that we're not exposing this dependent variable to, this other group, we should see not seeing the same level of decline. Now, okay, very good. So suppose that you do this experiment, and voila, the test group that was exposed to a whole bunch of the cell phone tower or radio frequency, they're starting to die off. Then it's exactly as your hypothesis predicted. So then you would publish this study, and you would say, I have a study here which seems to indicate that one factor which could be causing bee colony collapse disorder is the emission of widespread cell phone tower frequencies, as you can see here in this designed study that I published, and now you can read it. If that was to be done, then maybe the person thinks they've got the right explanation, and other members of the scientific community will now try to replicate the results by conducting similar experiments with slightly altered conditions. Now, if a bunch of people all find the same results with the same kind of experimental design, notwithstanding some edits or tweaks, then we would start to say this hypothesis is on the way to becoming a theory because it seems not to be contradicted by any of the tests that we have performed. So we think we're really getting the correct explanation here. But on the other hand, guys, and keep in mind, it's never a foregone conclusion whether your hypothesis will succeed because it's initially stated as a tentative possibility. So suppose you do the same type of experiment and another counterfactual case, there's no change at all. Maybe the group that's been affected by the radiation is actually healthier and dying less. I don't know. I don't want to complicate it too much. But let's just say there's no measurable difference in the survival, health, or other factors between the two test groups. If that was the case, then you would say, you know what, I don't think I've properly explained what's causing bee colony collapse disorder. So you would just ditch the whole cell phone frequency hypothesis, but you still have the same problem to be explained. We still don't know why. And if the question remains, then we keep working until we get some kind of hypothesis which is validated by the results of the testing. So eventually we'll get the right fit of hypothesis to testing result, and then we will get the confirmation that we want. But until then, it's just work for science to do. Now that process, that procedure of identifying some phenomena, trying to explain initially why it might be happening, eventually testing that proposition of your explanation to see if it's verified or not. This is the same method that we all use, which Sir Francis Bacon initially kind of laid down in Novus Organum, which was his classic book that initially described the scientific method to the West. This same procedure with these simple steps is the reason that you and I can talk through this, fascinating technology of the computer, why we can use telephones. So all technology is based on insight into the way that things work in nature and cause-effect relations that things have, which we discover through science. So it's not just magic that we have cars, telephones, video games, nuclear weapons or power or medicines or vaccines, because all of these things are the product of scientific research. So if you like the modern world that you're living in and you're happy to not just be a farmer, with no kind of electricity or technology of any kind, then you should have a certain sense of respect and gratitude for scientists, I meant to say, even though the original scientists were kind of like philosophers in a way, since it's like the master academic discipline, if you go back far enough into Western history. So anyway, talking about the steps of the scientific method, and those were all 4 or 5 rather. After that, and maybe I'll read a little bit from the book, you can see what they say. No, farmers are important people. Obviously I have total respect for farmers, but what I'm trying to say is that we live in a world today that I think is much more equipped for human purposes than the natural world that we would have found thousands of years ago. And yes, we know Mendel, the geneticist, and others in the history of Western science were actually very important. Agrarian farming and stuff was like the norm prior to the industrial era. So I would be writing a lot of people off. I was just trying to say that many of us probably prefer the trappings of modernism with all the nice things that we have, glasses, technology like this. It's just a harder life, I believe, living in a pre-modern world. But these are fair points, so I take it all on board. In the book, just a couple things from there on some of these steps, like 4 and 5. It says here, test the hypothesis. So after completing the observation and data collection and refining the hypothesis, the next step is to test the hypothesis. Testing may be done in a laboratory using a controlled experiment or in the real world. Louis Pasteur designed an experiment in which he inoculated 25 animals with a vaccine to determine the effectiveness of a vaccine that was made from anthrax germs. He also had a control group of 25 animals that did not receive the vaccine. And through scientific experimentation, he found that the vaccine was effective against anthrax. So just the way that we sometimes use animals to perform tests to determine the properties of specific chemicals or agents in the world. Testing a new hypothesis may take time if it depends on direct testing of empirical evidence that does not occur very often. For example, Einstein's theory of relativity predicted that the sun's gravitational pull would bend starlight. But to test that prediction, you need a real-world setting. You had to wait until there was actually a solar eclipse that provided the right conditions for seeing whether the predicted effect would happen. So sometimes you can have a controlled experiment in a lab, like I said, and in other cases, you're using the natural world and things that are happening in it to conduct your test. Finally, it says, the last step is to evaluate the hypothesis using testing and experimentation. If the results or findings don't support the hypothesis, then scientists will reject it and go back to step 2, come up with a new hypothesis, and repeat. Yeah, and about the bees. After 4 years of research into the cause of honeybee colony collapse, a 2010 study at Penn State College of Agriculture found unprecedented levels of a particular pesticide chemical in honeybees' pollen and hives. However, this hypothesis, while one of the most promising, has yet to be fully verified. The current hypothesis has been expanded to include multiple causes, including new and re-emerging pathogens, bee pests, environmental and nutritional stresses, and pesticides. So that's not exactly the most uniform hypothesis, but sometimes facts are complex in reality, and we have to accommodate that in the way that we explain things. Okay, so Yeah, maybe so. The harder life fosters invention and creativity. I mean, how to test this hypothesis is hard to know, but I guess we have enough anecdotal observation of the world to think that there's some truth to that. But we are standing on the shoulders, of the giants of the past who've led us to this point. Is this a quote of the who is his name? I don't even know this guy's name. This weird young little guy that doesn't have anything good to say. Yeah, something. This guy on the internet. I know you're talking about Noah, but forget his name. He's not that important. Okay, so let's keep going. Okay, so then, what we should say next are what are some qualities that good scientific hypotheses or theories will usually have. Because as you know, not all hypotheses are equal. Some are better suited to explaining the phenomena that they attempt to explain than others. So you want to be able to make those distinctions between a good or a not so good hypothesis or theory. So here we have qualities of a good scientific hypothesis or theory. I put hypothesis / theory because the distinction between them is a little fuzzy, obviously. I mean, a theory is just a very well-tested hypothesis, so I don't want to insist on one or the other term. Both distinctions can apply to the qualities mentioned here. Okay. Yes, those are good references, and I agree for the most part. I mean, there's a lot of genius work in the ancient world even. Never mind the early modern era, the Renaissance period, and then, of course, post-industrialization in the current day. So there's no monopoly on insight, wisdom, and like depth of character and insight in the modern time. It's just that we are sort of the lucky ones, I guess, living at the tail end of history to have inherited all of this knowledge that's come before. But good. What are some qualities of a good scientific hypothesis or theory? So one of them is simply this: relevance to the problem being studied. Relevance to the problem being studied. So, I mean, I feel like, in a way, this quality or criteria is so obvious that the book didn't necessarily need to mention it, but I mean, it does, and so I'll say this. Obviously, if you have a hypothesis, it has to be about the topic that you're trying to study. It should be related to the phenomenon that it's trying to explain. So, like, if you're trying to study something that's sociological and your hypothesis has something to do with, I don't know, something meteorological, then that would be an irrelevant hypothesis. Like, say that you're trying to explain why more people are getting divorced, because there has been a major increase in divorce rates. I think it's up right around 50% or more now than of couples that get married will eventually not be married in the end. So, and that's way different from like 100 years ago when marriage was much more likely to be predictive of your whole lifelong matrimony. So anyway, and yeah, Bill Gates himself, another one. Bezos also. So we've got a couple billionaires, I guess, with a little more, I don't know, freedom on their hands or something. They're outside their marriage at this point. But back to what I was saying, right? Marriage is an institution that seems in a way to be not as stable or solid as it used to be in terms of its durability. What could be the reason? Maybe somebody has this hypothesis. Well, global warming's happening, and so maybe that's leading all these couples to break up. But, you know, this is a pretty weak hypothesis. Maybe you could try and marshal some support for that, or try and, you know, craft some kind of evidence for this claim, but it's very unlikely to be correct because the two fields are unrelated. You know, sociological facts making up and breaking up isn't the same thing as weather patterns and, you know, the human activities or lack thereof that causes that. So this would be an irrelevant hypothesis to the problem that you're trying to explain. I think in a way it's obvious that you have to have a hypothesis that is relevant to the subject matter, but if it wasn't obvious, now we're making it explicit with this point here. Okay, so is Musk? I thought Musk was married to, what's her name? Grimes, the DJ or musician. But maybe they're not actually married and they're just in a relationship. Anyway, though, they had that kid, Aleph, or I can't remember the name, but it's like a weird name. Okay, so relevance to the problem under study. That's one of those. Another one is this: consistency with other well-established theories. Okay, so a good scientific theory or hypothesis should not contradict others that have already been well established and well proven before. So like a new hypothesis or theory that arrives into the scene of the scientific community should fit in well with and not contradict the other things that have come before. So let me put that here and I'll explain it in a little bit more detail. Will fit in with and not contradict other well proven theories. Okay, so to be consistent with other well-established theories means that it doesn't go against them, it doesn't invalidate or contradict them. I don't know if it's a crude enough metaphor, if it doesn't really capture the idea, but here's something to use as a concept or example. Think of science sort of as like a big jigsaw puzzle. And so like when a new piece is added to it, it has to fit in with the other pieces that are already there. It shouldn't be a piece that has no ability to fit in, and so you have to throw out all the other pieces to make room for it. Because when we talk about science, we often say that it's a body of consistent theories that are all supposed to meld together into one coherent whole. Sometimes scientists say that with each new generation of scientific research, we're standing on the shoulders of giants, meaning that we're not clearing away and rejecting everything that has come before, but we're building on top of it. So we just keep stacking new and further scientific knowledge and understanding onto the established base of knowledge that has come from before. So a good scientific theory then, or hypothesis, ideally should fit in with and not contradict these others. If your hypothesis requires you to make radical changes to the other theories that you think you already well understand, then perhaps push comes to shove, this is the wrong hypothesis. This is a perhaps overly simplistic example, but let me show you this as one possibility. So say that somebody, they see presents under their tree on Christmas morning, and their thought is maybe Santa delivered me these gifts. So my hypothesis to explain the observation of these gifts is that it was delivered by Santa according to the legend of Santa Claus. But if that was the right explanation, that Santa came and gave gifts, then let's consider what that means. I mean, if Santa delivers these gifts, that violates all kinds of other things that we think we know very well about physics and science. First of all, according to the myth, Santa flies around in a reindeer-driven sleigh all across the globe on Christmas Eve and into the early morning, delivering these gifts to everybody. But as you know, reindeer are terrestrial mammals, and so this would violate certain facts that we know about biology, about aerodynamics, and conservation of matter, I think, because if he had a bag that could actually hold all these gifts, then this would be like a magical bag that could somehow condense matter into something much smaller than it ought to be. And that would violate all kinds of other physical principles too. So if you want to have the Santa hypothesis, okay, but you're going to have to reject things that we think we know about gravity, thermodynamics, biology, and therefore it's not the best hypothesis. So a good hypothesis will fit well with what's come before. Now, let me say this. Can there ever be exceptions to this? It's possible. It's possible theoretically for there to be a revolutionary theory that does require us to discard some substantial body of evidence or knowledge that we thought we had before. As an example of that, there's Newton's laws, which are, for the most part, accurate and correct at describing the physical forces of nature. But when Einstein came around a couple hundred years later, the theory of relativity and the electrodynamics of moving bodies that he, published Nobel Prize-winning physics papers for in 1906, they show that there are certain technical aspects of Newtonian physics that are wrong. And the Einstein theory was much more predictive of physical outcomes in experiments. So therefore, it's not impossible, but it's like the exception rather than the rule that you will have a new theory that does legitimately require a force or revision to prior theories that we thought were well established. To do that, though, you need overwhelming evidence. So it's not the typical case. And Paul, you say this: if you reject a bag of holding, then you are rejecting the most fundamental tenet of Dungeons and Dragons, because you can have unlimited storage in a bag. Well, yeah, I don't know. I never played it that much, but I do like some of those turn-based RPG games like in video game land. So I just never really played with the actual cards and stuff. You have to have a community for that, and it's kind of like if you're too busy and stuff, you just don't find it. But I'm a big gamer, so I guess I put my energies elsewhere. So yeah, there you go. Let me read from the book on the same point. It says this: science is a system of logically consistent hypotheses or theories. Scientific explanations are preferred if they are consistent with well-established theories in the field, what American historian of science Thomas Kuhn refers to as normal science. This system forms a paradigm, a particular way of looking at and explaining the world. For example, the new hypothesis that internal processes in the ocean, such as the release of oceanic methane hydrate deposits that exist on the seafloor on continental margins, are the primary cause of global warming, is considered a good hypothesis by some environmental scientists since it is consistent with the established paradigm that global warming is the result of a combination of man-made and natural changes in the Earth. The intelligent design theory, on the other hand, this is just from the book, does not meet the criteria because it is inconsistent with the well-established theory of evolution. But scientists don't automatically discard explanations that contradict well-established theories if they do meet the other criteria for a good explanation and there's overwhelming evidence. And so then they talk about how Einstein's work did contradict some aspects of Newton's work. Okay, yeah, there you go. The neckbeards. Okay, I don't know. I mean, there's a lot of nice people out there that have these hobbies and stuff, but I kind of think I catch the reference there. So, okay, we can go to the next. Consistency with other well-established theories. Another highlight quality of a good scientific hypothesis. So then next we get to what's called simplicity. Quite interesting concept within science and philosophy of science. So simplicity is the overall term, but you're often going to see this referred to in academic discussions under the label of Occam's razor. So let me put that in parentheses below, just so you know the two different ways it's sometimes referred to. Occam's razor. Who's Occam? Okay, so there was a medieval philosopher named William of Occam, and he first proposed this concept, and so his legacy is that it's named after him pretty much now. So whether you call it simplicity or Occam's razor, here is the concept. That if you have two different available explanations for a given event, the simpler one that involves fewer assumptions is the one that is likelier to be true. And so the scientist will always prefer the simpler of two available explanations for the same event. Okay, so the simpler of two explanations is likelier to be true. So simpler of two, likelier to be true. It's a general assumption of science that somehow this universe is elegant and parsimonious. So it's sort of like reality, for whatever reason, seems to prefer the less complex or assumption-laden explanations for phenomena or events. This is perhaps not an ideal example, but I'll go with some in the book after this. Let's just try this one, though, to start. So suppose that you'd parked somewhere where you were driving, and you left and did whatever activity you were doing, coming back to your parking spot. You come back and now recognize that, wait a minute, my car's not there. So your car's not in its designated spot where you parked it. So that's a problem. Right now, you're like a miniature scientist trying to hypothesize what's the explanation for this identified problem I've observed, my car not being there. So let me hear from any of you. What do you think could be a reasonable initial hypothesis? What happened to this car? This has actually happened to me, so I can relate to it. But even if it hasn't, I think you can just imagine the situation hypothetically. So what might be your first initial thought? Where is this car? It's your car. You parked it there. Now it's not there. What could explain that? What could possibly explain that? I don't know. Don't have to be too creative, but it's not the most unrealistic possible situation. So let me hear it. What could be a reasonable sounding explanation, call it a hypothesis, to explain where it went? Okay, so it might be that someone stole it. Sure. And that's a fair hypothesis, Anthony or Noah. Maybe someone took your car and you've been the victim of, carjacking or theft. Well, carjacking is a little different. Isn't that when they you're held at gunpoint or you're forcibly removed from it? But anyway, it could be theft. That's one possibility. Okay, and then Mateo, you're already going for a very weird one, that the President of the United States got hungry and ate the car. He did look pretty big. I don't know if you saw this photo of him with the Carters that came out yesterday, looking like a tall tale, looked like Paul Bunyan. But yeah, and Paul, you say, I got back from travel and my car was in long-term parking at LAX. When I got back at 1 a.m. a few days later, I could not find my car there, so you assumed it was stolen. Okay, so that was your hypothesis in reality. And then you said, so I went to the LAX police department to report it, and it turned out to have been towed because my tag expired while you were gone. Oh my God, that's pretty funny. Yeah, so one hypothesis was theft. Another hypothesis could be parked in a marked stall or something like this that made it so that you could be towed. In my own case, it was a case of towing too, but I digress. So those are different hypotheses. Let me just give you one of those and then provide another alternative one. Mateo, you kind of almost beat me to the punch by giving such a weird one because I was going to make up a very weird one. But I'll give a different weird one of my own choosing, I guess. So let's use these two explanations. Explanation one, my car was towed away. Maybe it was towed. That's one explanation. Explanation two, space aliens came down from outer space and they abducted my car and took it away to, you know, whatever, the Andromeda galaxy or something. So we have alien abduction of the car, one hypothesis. Or it was towed, another hypothesis. I'm trying to make it pretty easy, so I think you can agree. Which of these two, they're both hypotheses for sure, but one of them is way simpler because one of them does not involve so many additional assumptions. Like for one of these hypotheses to be correct, you would have to make a whole bunch of extra assumptions that you don't have to make for the other one. So anyway then, which of the two do you think is simpler? Towing or alien abduction? It's easy enough, but just let me know that you comprehend. So which of those would be so-called simpler? I'm giving you two options. The simpler one, which one is it? You've got towing versus aliens. Well, the Rube Goldberg machine, yeah, that's more complicated, is like better in that case. But like still though, let's just say it one time so that it's clear in the record on this chat. To all here that are here, is this confusing? I hope it isn't. So I thought this was a real easy, like a softball for you. Just let me know which one was the simpler hypothesis, that it was towed or that it was stolen by aliens. Okay, you've seen weird stuff happen at night in Utah. Another funny joke. I get it. But obviously, the simpler explanation is the most likely. My question, though, is that which one is simpler? And towing is a simpler one, okay? But although I understand that you probably know that, I wanted you to say it. But let me make a couple additional points. Why is it that it's less simple to say it was stolen by aliens? Because what extra stuff do you have to assume? What are some additional assumptions that you now have to make to sustain the alien hypothesis? You would have to assume, for example, like what other stuff? For aliens to have been the explanation, you first of all have to obviously assume what? And none of these things have to be assumed for the other hypothesis. That's way simpler. But to support the alien one, you would have to assume that they exist, okay, that they first of all exist, which is not known. Then you'd have to assume not just that they exist, but that they're really highly intelligent. Because if aliens are stealing your car, then they're not just like, I don't know, little worms or bugs on the surface of like a moon rock somewhere, but they would have to be like highly intelligent life forms that have built interstellar transportation that can take them from whatever part of the cosmos they're in to the Earth. So we would have to assume that there are aliens outside of the planet Earth, that there's other life. We'd have to assume that they're extremely intelligent and advanced, and they have interstellar transportation methods that we don't even have. Then we would also have to assume that they take a special interest in your car for God knows what reason. So those are a whole bunch of extra assumptions. None of those have to be made to simply assume that it was towed. So in these two hypotheses, one is a clear winner. One is way simpler and therefore more straightforward and likelier to be correct. Yeah, and so let's see what are some examples in the book, maybe a little bit closer to home or more like ordinary. But I like the thing you said above there. What was it that the president ate the car? That would be another very weird and wild hypothesis that would be less simple than saying it was towed, because then you would have to say that the president is hungry for cars, then he can eat them, and that he takes an interest in your car, all kinds of weird assumptions that don't have to be made for the other case. So it says this: if rival hypotheses, like a different hypotheses or explanations, satisfy the other criteria, scientists generally accept the one that is simpler
a logical principle known as Occam's razor, named after the medieval philosopher William of Ockham. The great majority of scientists reject intelligent design theory because, among other reasons, the theory of evolution is simpler than that of intelligent design. The process of evolution can explain the gradual development of complex organs such as the human eye, beginning with light-sensitive cells that primitive organisms possess, and there will be therefore no need to add additional assumptions like the existence of a supernatural being that bears a relation to the natural universe. Okay, now the next quality or feature of a good scientific hypothesis is called falsifiability. Okay, so falsifiability. I don't know if this is counterintuitive, but it's just a fact that in science, you have to have a hypothesis that is capable of being proven false. If there's no way, even just theoretically, to prove that it's false, then it's not a scientific hypothesis because that means that you can't test it. Consider what it is to test a hypothesis. To put a hypothesis to a test is to expose it to a certain condition where it could be disconfirmed. Like in the hypothesis about bees dying off from radiation of cell phones, there's a way to show, at least through an experiment, that maybe that hypothesis is not correct if you perform the proper experiment and you don't see the results predicted by the hypothesis. That would be falsification of it. But this is good because it is only if it is falsifiable that it can even be tested. So if you don't know what would even count as this thing being false, then you can't test to see whether it's true either. Because testing for the truth of a claim requires awareness of what a falsification condition would be. Okay, so a good scientific theory is able to be proven false. And so falsifiability is the ability for it to somehow be proven false. Falsifiability. When a good scientific theory is capable of being proven false. Hypothesis/theory is capable of being proven false. Now, importantly, being falsifiable, being able to be disproven, does not mean that it will be disproven or that it is false. So some people might get confused, like, well, how is it a good thing if it could be proven false? I thought the whole thing was to prove that it's true. Yes, but to prove that it's true, or to at least be eligible for such proof, it has to be capable of being tested. And it's not testable until and unless you know what it would be that you would be looking for in the experiment in case it was false. Okay, and now, Paul, here's what you say. Some of Einstein's predictions didn't have a known test for it until much later. Yes, but he still said that here are the conditions which, when they arise, will provide the method by which you could do a test. So it's not that it's unfalsifiable, because even if the conditions are rare, they're still possible to have and to obtain. And you say this, just as some of his hypotheses contradicted Newton, they were also not able to be proven true or false until much later. Yes, but again, as I say, there was still a method of experimental verification and test awaiting the proper conditions to come later. I don't know if I would agree with you that it was a bad hypothesis, because just because the contingent factors that allow for falsification to exist don't yet arise, does not mean that you cannot package the hypothesis together with a description of what those conditions would have to be in order for the test to properly be conducted later. But anyway, I mean, it's a fair point. Let's say this, like unscientific and pseudoscientific stuff that's not testable violates this criteria. Take like the astrological predictions of the horoscopes. Those things are not falsifiable because they're stated in such vague and ambiguous language that they say nothing could be really given as a clear counterexample to the prediction. So if you saw in your horoscopes that it says you're going to be visited by a little friend next week, or an old friend will come to visit you, and then you're like, well, you know what? Nobody came, and I was just at home in my apartment the whole time, so that was false. The astrologist will not say, okay, fair enough, I guess I was wrong and that was the wrong prediction. They'll say, no, you just didn't look hard enough. You just didn't notice that that little bird that perched on your balcony was the friend that I was referring to. So now anything gets counted as confirmation, and nothing could possibly be counted as falsification. That means it's not a scientific theory because you're not being invited to test it. They don't say, don't take my word for it as just a given. perform an experiment, and the experiment can have a possibility of showing that it's false, but you won't see that. You understand? Like, that's not a scientific claim then if it cannot possibly be tested. And I'm not, yeah, and I guess what I am a Pisces, but back to what I was saying though, there are also outside the realm of astrology and pseudoscience like palm reading, crystal ball gazing, tarot cards. Outside of all that, there are even like some research that's been done by credible people that was not scientific because it was unfalsifiable. Like as an example, think of Freud and Freudian psychoanalysis. Now, a lot of people give Freud a lot of credit as being somehow the father of modern psychiatry and psychology, which is sort of true, but he also had a lot of weird and wild ideas that are not scientifically based because they're not falsifiable and therefore they're not testable. As some examples, right? He has all this kind of weird stuff about proto-sexual attitudes that he thinks little children, even infant children, have. So he thinks that, or he thought that like little boys in their early stages of life, they go through what's called the Oedipus complex, which is that they have a latent sexual attraction to the mother figure, which he claimed will play itself out in their later adult life as they seek out a partner that's somehow similar to their mom. And in little girls, he thought little girls have the Electra complex, which is the same but on the other side, that they have a latent sexual attraction to the father figure, which also plays itself out in adult life in the pursuit of a partner that's similar to that. But these are unscientific claims, because if you say to him, like to a Freudian, that is complete garbage, no way, there's no such thing as like latent sexual attraction that little children have, and I certainly didn't have that. Well, then he would say, oh, that's all that, you're just saying that because you suppressed it into your subconscious. So obviously you don't have the awareness of these proto-sexual attitudes because they're buried deep and submerged in your subconscious. But that means that nothing could possibly be given as a counterexample to what he's claiming. So he's not inviting us to perform realistic tests. And that's also what it says here in the book. He had a whole bunch of other stuff. I mean, the guy was using a lot of cocaine and everything. Back then, that drug, you know, was in Coca-Cola and other stuff. And so some people just thought it was like kind of like, I don't know, a tonic that helped you think better and be more, I don't know, active and stuff. But a lot of those weird ideas maybe are the result of the drug use more than this scientific acumen. But here's what this says. It says, on the other hand, theories that can accommodate all challenges have a critical weakness because they cannot be tested for being false. For example, Sigmund Freud's theories about the Oedipus complex fail the falsifiability criteria, since if a man claims that he doesn't have the complex, Freudians say that they've repressed it into their unconscious, and since unconscious thoughts cannot be tested, there's no way of falsifying his theory. So a good theory says here, if you want to see if it's false, just try to perform this test, and if this was the outcome, that would show it's false. But if you're not given any such an option, then that's an unscientific claim. And let me look at what y'all are saying a little bit. It hasn't been proven false, therefore it's true. Okay, if it cannot be proven false, then it can only be true given that fallacy. Yeah, it's kind of like that. I mean, in a way, it's saying here's a true claim, and not only it's not that it can't be proven false. It's just that the theorist doesn't even tell you what it counts to show that it's false. Like they don't provide any condition under which they say this would mean it's false. Okay, good. And if you had not used the term sexual, it wouldn't have been terribly wrong in the sense that we may create a model of what a good loner man is. Sure enough, but the devil's in the details, Paul, and he really does insist on this. In fact, he thought that this was like, you know, like a progressive idea because people were so closeted coming out of the Victorian age to talk about sex at all that he thought, you know, I'm getting to the truth, like things that people in polite society don't want to talk about. Everything's sexual. We're all sexual beings right down from the very beginning of our lives. And so I think he riffed on that a little bit too hard, and, you know, there's not a lot of scientific support for that. But some of his general ideas have been widely accepted, though, and have better confirmation. Okay, and then you can say one other quality of a good scientific hypothesis or theory. Well, let me read this last thing, though, from the previous notes. It says, a hypothesis or explanation should be presented in a form that is testable. Therefore, one of the main tasks of a scientist in testing hypothesis is the search for negative falsifying instances. For example, the hypothesis that all swans are white was based on the observation of hundreds of thousands of swans. Each one was white. However, the hypothesis was falsifiable since it would take only the one non-white swan to prove it false, which happened when black swans were discovered in Australia. Anyway, we shouldn't be resistant to falsification because if you don't allow for your theory to be in any way falsified, then it's not going to be capable of being tested in a scientific way. Okay, now one last quality of a good scientific hypothesis or theory is predictive power. And that is just when a good scientific theory can be used to accurately predict future events. So if you have a good hypothesis / theory, it should be able to make real accurate predictions of things that will happen later. Just as one clear enough example, take astronomy, not astrology, but astronomy, which can tell us specific dates and times that we should expect to see the next solar or lunar eclipse, or even what parts of the Earth's surface where you could stand on to have ideal viewing conditions to see like the complete or total lunar or solar eclipse. We know these dates, or the dates at which certain comets or asteroid showers will occur with great precision, months, years, sometimes even decades in advance. And then when the exact date and time occurs and the exact physical phenomena is observed, it grants credibility to the field of science that issues these predictions, because it seems like they make a prediction, and based on the scientific understanding of the concepts that they're describing, we see the predicted event happen. Weather and meteorology could be another case. When you see the weatherman give a prediction, we all know that it's not 100% accurate, but it's also not just like a wild guess or hunch that turns out to be inaccurate about half the time. I mean, there's a great degree of reliability there. So to the extent that they say, bring an umbrella because it'll rain on Saturday, and then it does, you can now repose a little bit more confidence that meteorology and the principles that it's founded on are sound scientific principles, because they do issue accurate predictions. So then last thing is this. I want to tell you guys what's pseudoscience. Pseudoscience is fake science. It's fake stuff that tries to look like it's science. And the way that the book puts it is this: pseudoscience. It is a body of explanations that masquerades as science in an attempt to appear legitimate. So it wants to appear to some people as like scientific or based on like methodology that's somehow rigid and rigorous, but it's only faking it. It's just masquerading, putting on the false appearance as science. That's the creative verbiage used in the book. So I'm just using the exact same. To masquerade is to put on a mask that will conceal your appearance from other people. So pseudoscience is like that. It's a body, it's a field of explanations that tries to appear to be scientific, but it's not falsifiable. It does not involve any kind of actual experiments conducted to prove the claims, and they provide no condition under which the claims could be somehow shown untrue. So what are some examples of pseudoscience? Let me just tell you, it's stuff like astrology, or crystal ball gazing, or palm reading, tarot cards. Some people I've seen doing this weird divination stuff with rods and trying to find water underground. Astrology, crystal ball, palm reading, tarot cards, and on and on. Pseudoscientific, some kinds of new agey stuff that cannot be validated in any kind of scientific investigation. So be careful not to fall for the false claims of pseudoscience. A lot of times people are profiting off of the fact that so many of us are yearning for something supernatural in the world, or something that gives us non-scientific answers to our problems. But a lot of these cases are just going to divest you of your money, enrich people that don't really have your best interests in mind. And it's mentioned in the book, and I'll close with this. Pseudoscience is a body of explanations that, in an attempt to gain legitimacy, masquerades as science. However, unlike science, in which explanations are grounded in scientific method, observation, reason, and testing, pseudoscience is based on emotion, superstition, and rhetoric. There's also numerology, psychic healing. While scientific explanations and hypotheses use precise wording, those of pseudoscience are framed in such vague language that it's impossible to determine what would count as verification and impossible to count what would count as falsification. So there you guys go. I don't know if I would say religion has to be a member of that same category, but you know, we all can make our own relative judgments, I suppose. It's not really that religion, I think, claims to be scientific. So there's that slight difference. There's like a value system and a belief system of religion, but it doesn't necessarily say, look, here are experiments that we have conducted, or here are like credible findings. But you see like these paranormal people, they'll show up to like a haunted house with tools that they say that they've used, and they have the like veneer, the facade of like some type of scientific rigor. But all right, guys, so I appreciate our meeting today and all the comments that we've had. I'm gonna have to let it go though, because I've got to start running the next stream for the upcoming class. But anyway, be ready on Thursday, and on Thursday I will distribute the quiz. So we won't have another one of our lectures on Thursday this week. It's quiz 3 on chapter 12. It's worth 100 points, unlike the other two, which were worth 50. So this one's a little bit more weight because it's the last of the 3 quizzes. So just study hard, read chapter 12, review the notes if you like, or the lectures,
and I'll distribute that on Thursday afternoon. Okay, then. So are we all good? Let me know so I can just get us going, and then I'll be in touch with you guys in the next few days. No, it is just chapter 12. It's not cumulative. It's only on chapter 12. It's just like, when we had a quiz on chapter 5, or when we had a quiz earlier, just kind of on chapter 1 and some related notes on logic. Okay, thanks so much. Very good. Have a great one, and I guess I'll see you guys soon. But wait, I still want other people to say goodbye. Come on, you just hang up with someone without saying goodbye? Say goodbye first, then I can end the stream. Okay, thank you, Jonah and Paul, everybody else. Good to see you guys again. Okay, so I'll see you back next week after we come back from the long weekend. All right, bye-bye. See you then.